Today, we want to start talking about our next big thing. If you recall, back at the beginning of the semester, we talked about two big questions that we deal with in calculus. Calculus is about the study of continuous change. Calculus is where we really start thinking in detail about infinity. And we frame that with two questions. What is the slope of the line tangent to a curve at a given point? That was the derivative question. That was the instantaneous rate of change question. And that's what we've been on about for the last 8 weeks, 7 weeks. Today, we want to start looking at the second big question in our framing, and that is area. So one of our big questions was, what is the area under a curve and above an interval? This is our next big thing. We usually just say area under the curve. So if you look up on Dr. YouTube, you're going to want to be looking for things like area under a curve. So just like so to draw a picture of this, we're talking about the area under a curve. So we'll have some curve and above an interval, let's say from A So we're just defining a top and a bottom for our region. We want under a curve and above an interval on the x-axis. So we just do under the curve and above an interval. This is the area that we're interested in. This is our starting point. We'll modify this to be under one curve and above another curve. But this is the core question. What's the area under a curve and above an interval? We are going to start with the easiest version of the curve. We're going to start by making the curve, requiring that our curve be defined by a function. Right now, we're studying calculus in the framework of functions. We're just using functions, derivatives of functions, and this is going to be integrals of functions. Because it makes our life easier if one variable is a function of the other variable. This doesn't always have to be the case, but it's the easiest case. It's like when you first start studying physics, you make sure stuff isn't going too fast so that you can do things like ignore air resistance. So here are the things that we have to deal with when we're dealing with this area question. Number one, what is our thinking? How is this a continuous thing? But what is our thinking, specifically our calculus thinking? How does that go? What are the mechanics of how this works? And finally, what is the point of doing this calculation? So the three things that we need to consider are the thinking. We need to think about the mechanics. And we need to think about the point. maybe point to something too graphical. Let's call it application. There's the thinking, there's the mechanics, and then there's the point behind this exercise. This is always the case. Anytime you do something in math, there's going to be some thinking behind it. Like this is the reason that we're thinking about this is how we're going to think about things. There's some mechanics, like all moving symbols around the page and how things are related to each other. And then there's the reason that we're doing this in the first place. Let's get about the thinking. Now, the thinking that has to come into play here is that since this is a calculus class, there's going to be some continuous change. There's going to be some continuous change, and continuous change shows up right at the beginning because we are trying to calculate an area, and we're going to go with the only area formula that we ever need, which is the idea of area. Area is length times width. That's it. That's just the idea of area. I'm just going to write it down like that. Area is length times width. This is the only area that we need. This is the only formula for area that we need. It's the only one. It's the very idea of area is there's length and some width, and we just multiply those two things together to get an area. All the other area formulas we know are just variations of this theme. If area is length times width, what if our thing is round? Then it's pi r squared. If area is length times width, then what if our thing is a triangle? Then it's 1/2 base times height. But it's all just variations on this. This is the idea of area. This is how we even define what area is. So this is area. What this requires is that the length is constant for the whole width. We get to multiply if the length is constant. So to calculate area, when calculating area, we get to multiply when the length is constant. When we're calculating area, we get to multiply when the length is constant. Let's think about what that looks like in functions. If I draw a width of 3, and my length is always, let's say, 5, To calculate area, we get to multiply because the length is constant over the entire width. Since the length is constant over the entire width, we get to multiply. So this is what I mean by length is constant, it's flat. So we get to do length times width. If the length is not constant, we don't get to multiply. We have to drop back to addition. If length is not constant, then we don't get to multiply. I'm going to use the same interval down here. But we're going to have different lengths. So for one unit, the length is, let's say, 4. And then over here, the length is going to be 5. And then on this last one, length is equal to 6. So in this example, length is not constant. We can't just multiply because we don't have 3 of one length. I don't have 3 of 5. I don't have 3 5s. I've got 1 4, 1 5, and 1 6. So I don't get to multiply. So in this scenario, I still might want this area. But length is not constant, so we don't get to multiply. Here, the length is variable. So we don't get to use multiplication. It's very clear what we do. We use addition. We don't have 3 copies of the same thing. So I can't just summarize my multiplication. I can't just say, oh, 3 5s just means 5 plus a 5 plus a 5. Multiplication is repeated addition. It's multiplication is addition where everything is the same. But here we don't get to do that because our area is going to be this first one, which is a 4. The second one is a 5, and the third one is a 6. So the reason that we get to multiply when length is constant is because multiplication is addition when everything is the same. Multiplication is addition when all the terms are the same. Multiplication is addition when the terms are the same. If the terms are not the same, that is, the terms are variable, we don't get to multiply, we have to use addition. This is not new. We did this way back in geometry. We wanted to find an area. All we had was length times width, and we had two different rectangles, or in this case, three different rectangles. We just dropped back to addition. We found each piece, and we just added them together. Questions? How's everybody okay? The reason that this is an easy problem back in geometry, and it's the reason I'm bringing it up today, is that this was a natural thing for us to do. It's because at that point in our lives, we had internalized the concept of addition. We have internalized the concept of addition. Everything else kind of fits on top of that. First, we learn to count, then we learn to add. Everything else is just an expansion of that concept. So where's the calculus in all this? This is still just a geometry problem, and we're not interested in geometry problems. Calculus is about the study of continuous change. So now, instead of our length being just different for a little while, where we get to use multiplication, we're going to take our length and we're going to make it continuously variable. Calculus and this next big thing, this integration thing, is what happens when we make the length continuously variable. So our original picture up at the top, the length is not only going to be variable, it's going to be continuously variable. In this case, we still want the area, but now the length is continuously variable. It's not just 4 for a while, then 5 for a while, then 6 for a while. When it looked like that, we could just use addition. But now it's whatever this value is down here. It's only 5 for one real number. It's 5 for a length of 0. Or sorry, it's a length of 5 for a width of 0. How do we add this up? There's a continuum. We can't add up all these heights because they're a width of 0. And it's a continuum. Where do we put the plus signs? That's the problem that we are encountering now. That's the calculus problem. Our length is not just variable, it's continuously variable. So there are 3 things that we do in math. Number 1, we add 0. Number 2, we multiply by 1. And number 3, we kick things back to an easier problem. And that's what we're going to do here. We're going to take this continuously variable thing, the problem that we've identified, length is continuously variable. We can deal with length being just variable. We just flatten it out for a little while, then we get to use multiply, then we go on to the next one, then we get to use multiply, and then we just add those 2 things together. We can cope with variable length. We need to deal with continuously variable length. We solve the continuously variable length by looking at just the variable length. Kick back to an easier problem. Do something that you know how to do. It's pretty much the solution that we always do when we get stuck. If we could either try to add 0, we can try to multiply by 1. Those are kind of like mechanical ways out of things. If we're trying to think about something to do, we just grab an easier problem that is similar and then modify things, which is kind of all we've ever been doing. So we're going to switch to a smaller problem. We're going to deal with the continuously variable problem by taking out the continuously parts. We're going to come up with a method that takes out the continuously parts. That just gives us variable. We're going to take out the continuously, and we're going to leave the variable because we know how to deal with variable. We deal with variable by just doing addition. Then we just apply calculus thinking, which is where things get weird, because we're going to have to cross that boundary from the discrete to the continuous. Discrete has all these convenient places to put plus signs. Continuous has nowhere to put the plus sign because there is no next real number. And in typical calculus fashion, we are totally just going to wave our hands at it. It's like, oh, then some stuff happens, and fundamental theorem of calculus. And you're like, oh, but what goes on in between? And I'm like, oh, fundamental theorem of calculus. And you're like, oh, but what goes on? Fundamental theorem of calculus is what happens. And so you just proof by authority to proof by authority, right? See, it's like kind of how it goes. Remember, this is all in the category of how we are thinking about the problem. It's about thinking about the problem. It's not about actually calculating the area. Actually calculating the area is just kind of one of the things that we do. It's about how we think about the problem. That's what we care about. So what do we do? So we need to talk about removing the continuously part and just leaving the variable part. So I didn't make it all that weirdly continuously variable. I made it very simply continuously variable. I realized that this is just a trapezoid. So we can just take the average of the bases, multiply by the height. Height is the one that's going this way, and we got the two variable bases. Secretly, this is on a logarithmic scale though, so it's not actually a trapezoid. I'm just kidding. I just needed something to change continuously. That's not going to cause me too much problems. Here's what we're going to do. Right now, f of x is continuously variable. That's our continuously variable length. This is a continuously variable length over our width from A to B. So what we're going to do is we're going to flatten out the function and make it just variable. And that's going to mean dividing our interval from A to B into smaller subintervals. Oh, of course I put 5. That's what I was trying to fix. So our strategy is going to divide the width for the interval from A to B, that's our width, into 3, in this case, subintervals. And then instead of having that variable length, I'm going to make it flat. We're going to divide the width into subintervals. In this case, we have 3 subintervals, all with equal width. That's just for convenience. So I'm going to say this is a delta x. And this width is a delta x. And this width is a delta x. To each of these subintervals, I'm going to pick one value from the function on each of those subintervals. Pick a value from the function on each subinterval. We're going to pick one value from each subinterval. So x1, here is x2, here is x3. We're going to pick one value from each subinterval. That's a representative of that subinterval. We evaluate the function there. That's going to be the height for that whole subinterval. It's representative democracy right here. From that district, that first delta x district, they elect one value from that district to represent the whole district. The function evaluated at those points. The function evaluated at the representative points is the height for each subinterval. We have removed the continuously variable part in favor of just variable. This is the thinking behind what's going on. So now our approximate area is the approximate area of these three rectangles. In this case, with our three intervals, that area, this first rectangle is the function evaluated as the first representative times the delta x. And then we have the second representative times the delta x. And then the third representative times the delta x. We still have the variable part. We took out the continuously variable part. We can see that there is some area that's missing from each interval. and there's some area that's included in each interval. So we've got a little bit of this overestimate, but we've also got a little bit of underestimate. We got a little bit of overestimate. We got a little bit of underestimate. I know I drew a line, so those will balance out if I put X1 in the middle. That's not always going to be the case. Stop thinking about averages all the time. Averages are trash. But this is an approximation of the area. The sum of these three rectangles will be an approximation of the area. The reason I wanted delta x to be all the same is that I wanted that delta x to be able to show up in all the terms so I could factor it out, reduce my calculation. That's just a convenience thing. They don't have to be all the same. How can we improve this approximation? What would we do? Right now I have 3 subintervals. What would make a better approximation? If by your silence you mean more subintervals, you are absolutely correct. Because that's what we do in calculus. We just like, well, here's how we do an approximation. It's like, well, let's just do that more. So more subintervals. Now let's say improve approximation. Right now we're doing an approximation. We'll improve the approximation with more subintervals. Uncool of me to expect anybody to answer a question on a Monday. It's like Monday morning. So I'm like, oh, what is 2 plus 3? And everybody's like, oh, no. It's Monday, dude. We do not answer questions on Monday. Not at least verbally. We're going to have some notation. I'm going to write this with summation notation. This is the sum of f at xi times delta x. This is for I equals 1, 2, and 3. So we'll say I is 1 to 3. This is summation notation or sigma notation, because that is a capital sigma. We use capital sigma for a summation. This is the sum as I goes from 1 to 3 of that means take this expression f at xi delta x, evaluate it for I equals 1, 2, and 3. and then add the results. We improve the approximation by using more subintervals. Maybe we use 10 intervals. So I'd write the sum as I goes from 1 to 10 of f at xi delta x. Maybe we improve it by using 100 subintervals. What would calculus say to do? How many subintervals should we do? 1,000? 1,000,000? 1,000,000,000? 100 billion? That's a reference to a movie that's older than all of them. Doing this more means a better approximation. So let's just do this infinitely more. At this point, you'd be like, oh, dude, that's back at our original problem of continuously variable. This is how we're coming at continuously variable. We need to phrase it in terms that calculus can understand, because we understand how calculus works. We need to phrase it in terms that calculus mechanics will understand, and this is how we get at that continuously variable. We improve the approximation with more subintervals. So calculus says use infinite number of subintervals. So we can't just plug in infinity because we have to have a number. We're like numbering things, right? So we're going to say, we're going to use n subintervals. And to use infinite number of subintervals, we just take the limit as n goes to infinity. Any questions? This is the thinking. This is how we get at continuously variable. We make it just variable, and then we start approximating the continuous. This is the area version of finding the slope of the tangent line by saying finding the slope of the secant line and just bringing those 2 points infinitely close together. Here we're just using an infinite number of intervals. Now the weird thing is that this delta x, they're becoming infinitely thin, but they're clearly not becoming 0, because if the width is 0, then we just get 0. And we can clearly see that there is definitely some area here. So there's an infinite number of rectangles. They are infinitely thin, but not 0 width. So that's weird. But this is how we deal with the continuously variable parts. What we're trying to do is is multiply. Area is equal to length times width, but the length is continuously variable. Any questions? We're going to talk about the calculus mechanics part of this. This is just the thinking that's running behind it. All right, that's going to do it for today. Stop thinking about this now. Actively stop thinking about this. I know that's easier done than said. So stop actively thinking about this. Let this go, and we'll get into mechanics tomorrow. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Thank you.